In this video, we're going to work through the problems from the Chapter 7 slides. So with Chapter 7, we're working on covalent bonding. So the first thing you need to make sure you can do is tell the difference between ionic and covalent molecules. So remember, with ionic, you need to have a metal in your formula. And with your covalent, it's all nonmetals. So the quick check is in your formula, do you have a metal or not? So for number 1, carbon and chlorine are both nonmetals, so this is going to be a covalent molecule. For number 2, we have calcium, which is a metal, so that means this is ionic. Number 3, we have iron, which is also a metal, so this is ionic. Number 4, phosphorus and oxygen are both nonmetals, so this is covalent. Go ahead and pause your video, work through numbers 5, 6, and 7 on your own, and when you come back, you will have the answers to those 3 problems. 6 and 7, go ahead and check those, and then we will move on. The next thing we did in Chapter 7 was naming our covalent molecules. So with covalent, we will have a prefix that indicates the number of atoms of each type of element that is in our formula. The one exception in using the prefixes is that you do not use mono on the first element. So for number 1, there is 1 sulfur, so we simply say sulfur. We have 2 oxygen atoms, so the prefix for 2 is di. For the second element, the ending becomes "ide," so oxygen becomes oxide. Four, 5, and 6. We have dinitrogen monoxide, dichloride heptaoxide, and sulfur hexafluoride. To go from name to formula, it is actually quite simple because the name tells you exactly what is in your formula. So carbon with no prefix means 1 carbon. Disulfide, we've got sulfur and 2 of them. Boron, no prefix, is just 1 boron. Tribromide, so we have bromine, and there are 3. Dinitrogen, 2 nitrogen atoms. Pentoxide, penta is the prefix for 5, so we have 5 of those. Silicon, no prefix, 1. Tetrachloride, we have chlorine atoms, and there are 4. Next portion was to talk about Lewis structures, starting with the Lewis structure of an atom. So here's where you need your group number. Group number equals valence electrons. And remember, group number, we're doing the 1 through 8 numbering system, the Roman numeral numbers. That is the number that equates to your valence electrons. So carbon is in group 4. The other thing when we're doing these is we want to use that box method. So we think about having 4 sides. We'll put 1 electron on each side first, and this is going to help us determine which electrons are by themselves, unpaired electrons, and which ones are paired. So carbon with 4, that's what it's going to look like. Nitrogen is in group 5, so we'll put 1 on each side first, which then puts the 5th one as a pair. Oxygen's in group 6. And then fluorine is in group 7. So work through the second row of elements and see what you can come up with for their Lewis structures. There are your Lewis structures for the second row here. Notice that there's a pattern. Both silicon and carbon are in group 4, so they've got the 4 unpaired. Nitrogen, phosphorus are in group 5, so you've got a lone pair and 3 unpaired, group 6 and group 7. So here's an extra naming slide in your notes. So again, go through and work these on your own. Check your answers. Remember, these were mixed together, mixed ionic and covalent. So first you need to remember which one's which. For ionic naming, there are no prefixes. So I kind of almost fell into the trap here for the second one. You have to only use the names of the elements for ionic. If you need to, go back and review chapter 7 for those rules. All right, back to drawing Lewis structures. Here are some molecules that we're going to draw Lewis structures for. And our steps for drawing Lewis structures with molecules, the first thing that you need to do is count your valence electrons. So this is group number again. AS is in group 3, so it's going to give us 3 valence electrons. Hydrogen is in group 1, but I've got 3 of them. So that means total I have 8 valence electrons. Next step is to decide what element is in the middle. It's going to be the one with the fewest valence electrons, with the exception of hydrogen. Hydrogen is never in the middle, so that means we will put AS in the middle in this case. Then you're going to attach all of your other atoms with single bonds to the middle atom. Remember, each line, which is a single bond, represents 2 electrons. So 3 single bonds here means I've used 6 valence electrons so far, which leaves me with 2. The next step then is to use those remaining electrons as lone pairs on the outer atoms first to make sure everything has an octet. For hydrogen, a full octet is only 2 electrons. So each of the hydrogens in this molecule right now already has 2 electrons to count, so those octets are full. The next step then, if you still have electrons left over, which we do, is to put them as lone pairs on the middle to make full octets. So there's those last 2 electrons. Then if we check AS, AS now has 6 electrons from the bonds and the 2 from the lone pair, which is also 8. So there is your final structure for AS3. Let's look at number 2. Carbon is in group 4. Hydrogen, again, is in group 1, and there's 4 of them. So we have 8 electrons. Carbon goes in the middle because hydrogen never does. We'll attach the 4 hydrogens with single bonds. Those 4 single bonds were the 8 electrons that we had, so we are now out of electrons. Let's check to make sure everything has a full octet. So each hydrogen has 2 electrons from the bonds, so that's a full octet. Carbon has 4 single bonds, which is 8, so that is your final structure for CH4. Let's look at number 4. We're going to let you come back and do number 3 on your own. So number 4, carbon has 4, oxygen has 6, and there's 2 of them, so that is a total of 16 electrons. This time carbon is the one with the fewest valence electrons, so it will go in the middle. I will attach the oxygens with single bonds. Those 2 single bonds took 4 electrons, so it means I have 12 left. We will put them as lone pairs on the outer atoms first. So there's 6, there's another 6, so that's the 12, which means I'm out of electrons. I have given both oxygens full octets, so that's why I gave each of them the 6 electrons. Now if I check carbon, carbon currently only has 4 electrons, the 2 from each bond, so it needs 4 more. However, I cannot add more electrons because I'm out of them. So what I can do is I can take lone pairs that are currently only in oxygen's count and move them in so that carbon can also count them. And this is how and why we make double and triple bonds. So if I move that first lone pair that I indicated, and it doesn't matter which one in this case, both oxygens are the same, all the lone pairs are the same, this is what I will end up with. So now carbon has 6 electrons, all of the oxygens still have 8. But since carbon only has 6, it again needs 2 more. So I could either take 2 more from the left oxygen and make a triple bond, or I could take 2 from the right oxygen and make a second double bond. When you have choices like this, always go towards what will make a symmetric molecule. So I'm going to make 2 double bonds leaving both oxygens with 2 lone pairs. Now everything has a full octet, and I used the 16 electrons that I had to start. So here is your final structure for CO2. Go ahead and work through numbers 3, 5, and 6, which are those that are left. For number 5, you do have a charge. So remember, charge, negative charge means extra electrons. So when you're doing your electron count, you're going to add 1 more to your total. Here's for Cn minus, H2O, and SO3. Here are a few more structures. Again, pause your video, come back, and see what your answers are supposed to be. Here's for pH3, NO2 with a -1 charge, and SiO2. All right, after Lewis structures, we started talking about molecular shape. To determine molecular shape, you need a proper Lewis structure, and then you will count the bonding groups, which is equal to the number of bonds, any type. So single, double, triple all count as a bonding group. Number of lone pairs, you just count directly from your molecule, but it's only the ones on the middle atom.